Hi, I'm Evan from Kestrel AI. Today I want to show a common misconfiguration that can occur in organizations that use Kubernetes but quickly realize not everyone understands how it works. A software engineer pushes a new service. They have not used Kubernetes too much in their career, so they either generate a Helm template using ChatGPT, or they pull an existing template from somewhere else, like a different service that they've worked on but they don't own. A platform team then reviews the new service before it goes to production, and they notice something weird. There's a pod anti-affinity configured. They assume the developer set that for a reason because nothing about the Helm template seems off, so they push it through. The service makes it onto dev with no problems. Then a week passes, it goes to staging with no problems. So at this point, the platform team seems like they're pretty confident that it can go to production. The problem is the way they configured it creates a ticking time bomb, and it's not going to go off until the worst possible moment, when there's a huge traffic spike in production. So let me show you what I mean. I've got an EKS cluster here with 4 nodes. So let me just show you that. So you can see there are 4 nodes in US Bus 2. And I've got a payments API service running here. So I'll show you that. So we have 2 pods right now and a load generator. So right now it's running fine with a couple replicas, but let's look at how it's configured. So I'm going to take this command, I'll copy and paste it. And what you're going to see here is required during scheduling, ignored during execution. The team used required, a hard constraint, because they probably wanted to guarantee that no 2 payment pods ever land on the same node. But here's what they didn't realize. Required means the scheduler will never co-locate pods, no matter what. If you run out of nodes, new pods just don't get scheduled, period. Now, why is that problematic? So let's actually simulate a traffic spike. Let's like the HPA kicks in and tries to scale from 2 to 8 replicas. So let me just manually have that scale. Okay, so now what we're going to do is we're going to, again, look at the pods and we're going to wait for them to come up here. So what you'll see is it's going to be able to scale to about 4 replicas for the payments API. But past that, it's going to run into problems. To showcase that, we'll look at the events. So you're going to see there's a bunch of failed scheduling errors. 0 out of 4 nodes are available, 4 nodes, no preemption, all this stuff. So the irony here is painful. Anti-affinity was added to improve resilience. Instead, it's causing an outage during the exact moment it was supposed to protect us against. It was supposed to make the payment API pods extremely stable, not dependent on node failures or anything, but now it's causing all these issues. So this is exactly what Kestrel catches automatically. And let's take a look. It's detected a rollout failure incident. So let's go ahead and take a look at one of these. So as you can see, the root cause that it's determined is exactly what we're expecting. The required pod anti-affinity rule caused the scheduling failures because the hard constraint prevents co-locating pods. This isn't just pattern matching, it's actually reasoning about the problem. So Kestrel doesn't just tell you what's wrong, it tells you how to fix it. It gives you all this awesome information like chain of events, the root cause, what affected resources. It gives you a recommendation as to what it thinks you should do. But the great thing is it also gives you the exact remediation in YAML here on how to fix it. So you'll see it changes the pod affinity from required during scheduling, ignored during execution, to preferred during scheduling, ignored during execution, to relax the strict anti-affinity rules, which is exactly what we need. So if you look at the difference, you'll be able to see that kind of stuff here. So the point of this is this misconfiguration sat there for who knows how long. It passed code review. It got through the platform team. It worked fine in dev and staging. The first time anyone who's seen this was during a production traffic spike. And Kestrel caught it the moment it became a problem, explained why, and gave us a fix, which eliminated any 2 a.m. debugging sessions for anyone who got woken up. So that's Kestrel. And that's why we're really excited about it. And the link to the demo repo will be in the description. Thank you for watching.